Then this is principally wrong because we are considering here a point charge, and we know that a point charge cannot constitute a current because current is combination of charges which are flowing in a unit time. So that's the reason that we can write in the terminology equivalent dimensions like this, but it is not substituting, or it is not making current because it's a point charge. So that's why this result is principally not right or equivalent to this result here, where we do take the integration of this. And also, there are relativistic effects that it may be true for this reason when V is very, very less than C, the non-relativistic situation. But if it would be the relativistic situation, then a problem will occur here because V, if it becomes comparable to the speed of light and that retardation, etc., will cause a problem here. So principally, this is not equivalent to this thing, is point charge cannot constitute a steady current. Now we will move to the divergence in curl of B. What the divergence in curl of B will give us. Now we start with section 5.3, and section 5.3 is the divergence in curl of B. Like we will find the divergence of B and the curl of B. First we start with the curl of B is, we already know that the divergence of B is equal to 0. We don't have a magnetic monopole, and when you don't have a magnetic monopole, then for a dipole the lines will converge and they will not diverge at all, and the divergence of B is equal to 0. And later on we will discuss that thing, that why the divergence of B comes out to be 0, and we will derive that thing. But here we first focus on the curl of B. So if for example I take an infinite wire, this wire, and this wire is carrying current. So if the wire is coming out of the board, the magnetic field is going around it because current in this direction, so magnetic field will go in this direction. So here we will find the magnetic field at a distance s. We have already derived this thing. So the magnetic field around a closed path, of radius means the path of the circle, or the radius of the circle on which we are going is S, then the magnetic field B is equal to mu naught I, the float current in 2 pi S. This is the value of the magnetic field. Now, if I do integrate this magnetic field around the whole closed path, then this implies that integral on a closed loop in B dot dl, because dl is the fraction of length around that loop. So B dot dl, this is equal to closed path integral, and for B I write mu naught I, and this is over 2 pi s, and about dl. Now the direction in which B is, the direction in which B is, the DL is also along the direction. So the angle is 0 and cos of 0 is 1. So we will write BDL cos of 0 and here DL will occur. And then this thing is equal to this closed path integral mu naught I 2 pi s will come outside and DL will make the circumference of the circle and that will be 2 pi s. So we have mu naught I over 2 pi s and here DL will also give 2 pi s and the B will come out, B dot DL will come out to be mu naught I. So this is very astonishing result in the sense that it comes out to be independent of S mu naught I. B dot dl around a closed path comes out to be independent of this. So if I do it dimensionally, then B times dl, it will give you length, and that length comes here, so it is again mu naught I over S. So it is the same thing, 2 pi s from here, so dimensions of length here, so magnetic field is the same. Now why this one came out independent of this? Now why this thing came out independent of S? Because the way S is increasing, so the same way the circumference is increasing. So both are cancelling each other, and here we are having mu naught I. Now there is one question here, so I can write this in a simple form is B dot dl mu naught I. Now here is a simple question that whether it is necessary that from a line we should have exactly a circular loop. What if the loop is not exactly circular? Then what will happen? And we are addressing this thing that if there will be in arbitrary shape of the loop and the current is passing through that loop here, like the loop is enclosing that current, then what will happen? So the result will be the same, because for that one, let me use the cylindrical coordinates, then I can write that the magnetic field can be written as B and its vector and mu naught I over 2 pi s, and it will be in phi unit vector. Because for a cylindrical system, I know that we are having our coordinates is s, phi, and z. This is for cylinder, and the one which the coordinate that goes around is phi. So B is in the phi unit vector here. And what about the dl here? The length element dl will be ds and s unit vector and s d phi and phi unit vector, s d phi and phi unit vector, and dz and z unit vector. This is the length element, and when I do multiply b dot dl, so this implies that closed loop integral b dot dl is equal to closed path integral and mu naught I over 2 pi s phi unit vector dot, then it will be dl, so ds s unit vector with phi unit vector will become 0 because they are perpendicular to each other. With this one, it will give you the s d phi and phi unit vector. It will be in the same direction, so it will give you 1 here, while with this one, it will again give 0. So we only write here the non-zero term we are not writing, so the zero terms we are not writing. So this is integral on a closed path, and we have mu naught I over 2 pi s here. And what about this one? This will be phi by unit vector will become 1, and s will be here, and then d phi. So s and d phi. Now, this d phi, when you integrate on a whole loop, then it will run from 0 to 2 pi. So this d phi will run from 0 to 2 pi, then it will give you 2 pi here. So 2 pi s, and the 2 pi s will cancel again with this 2 pi, and we will get that b dot dl again the same, even for arbitrary loop, this is equal to mu naught I, even for an arbitrary loop there. Now if we are having a bunch of wires, current carrying wires, and then this loop is enclosing them, one or two or more or all of the wire it is enclosing. So whatever is the enclosed current will be basically the total current. So whatever current it will enclose is the total current, and I will write this thing B dot dl is the current enclosed. All the enclosed current will contribute to the magnetic field. So B dot dl will be equal to mu naught and I enclosed. Now if, for example, the loop is not enclosing any current, then phi will run from, let's say, phi 1 to phi 2, and as no current is enclosed, so from phi 1 to phi 2 it will be the same thing, and we will have the same value phi minus phi, and it will come out to be 0 there if it is not enclosing any current. But what if it is enclosing some current? The current enclosed in terms of the current density, I can write that the enclosed current is equal to the J dot dA. This will give us the total enclosed current, and then I know the law, the curl theorem, or the Stokes theorem. I know that if of any vector I take the dot, this del cross V dot dA in its any vector V, then this will be equal to a closed path in V dot dl. Like you take the curl and is a dot product with the surface element, then it is the same if you go around a closed path, means that V goes directly around the closed path. So if I look here, B dot dl, instead of B I have V there, so V dot dl, so B dot dl can be written is B dot dl can be written as del cross B and dot dA and this is equal to mu naught. And for enclosed current, I can write J dot dA. And now, if I look here, then here the dA, the surface area, that is the same as here because it's the same area. So the area is basically cancelling with the area here, and I will have the differential form of this, the curl. So curl of B equals mu naught in J. Now with J I don't need to write the enclosed because it is the total current here, and this gives us basically the Ampere's law here. This is called the Ampere's law, and here this is the integral form of Ampere's law, and this is the differential form of Ampere's law. So B dot dl closed loop integral equal mu naught I enclosed, and del cross B is equal to mu naught J in differential form. And now if I look at the analogy of this thing with the electric field situation is what we did Gauss's law is earlier. I said that Gauss's law is basically it's analogous thing in magnetostatic is the Ampere's law. So now look at the Gauss's law. Gauss's law was a closed surface integral in E dot dA was equal to, so here B dot dl, here E dot dA, and here mu naught, so we were here in I enclosed, we were having Q enclosed over epsilon naught is, mu naught is direct proportionality, epsilon naught is inverse proportionality to the electric field. And then we converted this thing to the differential form, and it was it is dot dA, here it is dl, here it is dA. So it came out to be the divergence of electric field is equal to, for J I write rho because the equivalent is rho, and for mu naught direct proportionality, in here it is inverse proportionality. So this is the electrical counterpart of this Ampere's law, and this is Gauss's law that we have derived earlier. And from the analogies, from the symmetry, from the resemblance, we can see that the magnetic field curls, and how much it curls, it depends on the magnitude of the current density, and the electric field diverge, and it depends on the magnitude of the charge density. Epsilon naught and mu naught, they are the permeabilities and the permittivities we have. Similarly here, the resemblance is also evident. So with this, we are done with the curl of P, and now we will start with the divergence of P, that why it comes out to be 0.